So let's begin the talk. Happy to introduce Professor Kyu-Hwan Lee at University of Connecticut. He's going to talk about autocorrelation functions of Sato Tate distributions and identities of symplectic characters.
Okay, thank you for the invitation and thank you for coming. Thank you all for coming. Okay, this is a joint work with the Se-jin Oh. Se-jin Oh is there, sitting there. So let me start with the elliptic curve, but I will not talk about murmuration at all. So prefer murmuration. Prefer the discovery. This work is before the discovery of murmuration. Consider an elliptic curve defined over Q, and it can be given as a kind of cubic equation. And then for each prime P, consider the equation modulo P, and then count the number of solutions. That's called the number of solutions NP, which denotes the number of solutions by NP. And for small primes, it's easy to count the number of solutions because if P is 5, for example, then basically there are 25 possibilities. You can substitute one by one, count the number of solutions. Okay, but so this number is of course important because it counts the number of solutions and it is related to the arithmetic property of this elliptic curve. And in number theory here, we are very interested in these numbers. Because the NP will grow, really, because if P is very big, size is about 1 million, then obviously the number of rational points will be also big. So it is better for many reasons to consider this number AP, which is the deviation from P plus 1. Then it is known that the average is of AP is 0. Then it's natural to consider this because this will be a nice scaling. And it can be positive or negative. It's a deviation from P plus 1. So for example, the same elliptic curve, then A2 is 0, A3 is 0, negative 3, and A7 is 3. Okay, so this is a good normalization. And there are other reasons why we consider this AP. But yeah, let's just consider this as a definition that we consider this. Okay, then what is Sato Tate distribution? We fix an elliptic curve. So we consider one elliptic curve and consider AP as a just data set. And if we have a data set and we are interested in the average, then what's the next thing? In statistics, average, and then variance, etc. So AP is again this. And then it is known that AP is in this range. So in statistics, we usually normalize this. I mean, so it may be not statistics. Just look at this then. It is a good idea to divide this by square root of P. It will be from negative 2 to 2. It may be easier. Okay, and then it is known that the average is 0. So then why don't we consider the average and the variance of these numbers? And that was a very natural question, natural consideration in this setting, and then in the study of elliptic curves. But more generally, we want to describe the distribution completely. Then we remember that whenever you have a random variable, how do you describe the distribution? There are many different ways. One way is you consider all the moments, not only the average and variance. Variance is basically expectation of x squared, and then it is related, as you know. but the third moment, that's called the second moment, the third moment, and nth moment. So if you know all these moments, then basically you know the distribution. Okay, and then you can consider like a moment generating function and etc. So that's a very standard approach to describe the distribution probability. So we want to do that, but this is a discrete set. So this will be a good, the right definition, but for some technical reason, we only consider prime P where the elliptic curve has a good reduction because for finite number of primes, E has a bad reduction, meaning that it becomes a singular curve. So we want to avoid the kind of a singular phenomenon. So we only consider a good reduction. Then, yes, and then almost all primes have are good primes where the elliptic curve has a good reduction, almost all primes. And then we consider this finite set for some big N and calculate this mth like power because we are interested in this for OM. And then we divide it by the number of primes. Okay, then it's exactly the expectation of this mth power. And then because this is an infinite set, we take the limit. Okay, then this is the natural definition of mth moments for this set. Okay, so we are studying the kind of statistics of these numbers. Okay. And then what will be the result? Of course, people studied this a long time ago, and then they calculated it. And it was striking that for an arbitrary non-CM curve, so anyway, so genetically, you can choose an arbitrary elliptic curve. Of course, technically it should be non-CM, but arbitrary, but genetically it's non-CM. So, and then if you compute this, then empirically you see these numbers. And then here, interesting thing is you can choose any elliptic curve. So it can be a very big, like a rank 29 curve, or it can be just a rank 0 curve. It doesn't matter. So after like calculating enough, you see this. This is approximately, but empirically, but they observed this. Okay, this is very interesting because again, this is quite surprising that arbitrary elliptic curve gives us the same distribution, and this is very deep at the same time. So and then, but let's move from that arithmetic question, and let's just think about it like algebraically, combinatorially, and representation theoretically. And have you ever seen these numbers? Yeah, of course, yes. So these are Catalan numbers. Okay, and then there are more than, as you know, more than 200 different interpretations of Catalan numbers. Then one of the characterization is combinatorial. It's not really combinatorial, but one of the characterization of these numbers is they appear they appear as moments of a random variable when we study random matrices of SU2. Because we are interested in moments, and these are from moments. So this may be a good connection. So even though there are 200 different interpretations, this may be related to in our situation. So let's think about this further. So what's the meaning of this? So now completely away from arithmetic for the time being, and consider SU2, and then give you the probability measure on SU2. So the total measure is 1, the Haar measure. And then consider an arbitrary matrix, a random matrix. Then X is the trace of the matrix. Then this is a random variable. And if whenever you have a random variable, again, you are interested in the moments. So what's the computation of the moments here? It's an infinite group. So yeah, this is the definition of the moments. So random variable or trace of gamma, and then mth power, and then you take the sum integration, and then the number of elements is normalized as like Haar measure is the probability measure. It's the normalization, so we don't need to divide it by anything. So this is exactly the mth moments. Okay, then we are interested in this, and how can we compute this? Of course, SU2 has some coordinates, and it will be how many variables? 3 variables. So you can do integration. Yeah, and then of course you can do a good exercise in multivariable calculus. On the other hand, yeah, we can use representation theory, obviously. Let's use representation theory to compute these numbers. All of these are the very basic computations. But anyway, we'll use the representation theory. Okay, then, yeah. The starting point is, of course, the trace of gamma is the character of the natural representation of SU2. And then if you consider the Lie algebra and then SU2 and then SL2, the Lie algebra SL2 have the same representation. So yeah, you may consider SL2 representation. And then the mth power means basically you're considering this mth tens product. And then we remember from representation theory. So if you integrate the character over the whole group, then we have 0 because characters are basically symmetric. So you get 0. But when chi is trivial, then of course you get 1. Because the whole 1 is 1. The measure of the whole group is 1. So for all the other non-trivial characters, irreducible characters, you have 0. Okay, then what can we do? So write this the mth tensor product as the sum of irreducible representations. If you just consider irreducible characters, then write this character as the sum of irreducible characters. And then that's the same as decomposing the tensor product into irreducible representations. And then because all the other representations will go away after the integration, you just count the number of trivial representations. Okay, that's enough. So all of a sudden, the integration problem, multivariable calculus problem, becomes this decomposition of tensor product and then counting number of trivial representations. They are the same. So multiplicity, let's call it Tm. T of M is the definition. Okay, then yeah, the conclusion is this. So actually, you don't need to do any multivariable calculus. It's just representation theory. It says that this is the answer. Okay, then how can you do the decomposition? And of course, here the notation is V1 is the two-dimensional standard representation. And then M, let's call it V sub n, m plus one dimensional representation of SL2. SL2 and then SU2, the Lie algebra of SU2, SL2C. So you can just consider this. Then, of course, yeah, we have this Cauchy-Gordon formula from section 7 or chapter 7 of Humphreys. So we know this very well. Okay, so M then it produces m minus 1 and m plus 1. Okay, m becomes after tensor product of a v1 and minus 1 m plus 1. Okay, then let's make it into a diagram. Diagram will be like this. So here, this is the first power v1 basically. The m is this. After you tensor this with a v1 like this, so one copy of v2 and one copy of v0. Okay, and but because you move inductively, so next step will be this 2 means you add these 2. This 3 comes from adding these 2 numbers. Now, of course, it's getting bigger and bigger. So 14 and 14, 28. So this explicitly explains what's happening. And then here we are interested in the multiplicity of trivial representations, and then we get these numbers. And if you look at it in a different way, then these numbers count number of die-paths. Anyway, so there you can bring many different combinatorial interpretations. And then we have these Catalan numbers. Okay. It was like interesting fact. So we obtained exactly the same sequence in this computation. And clearly, this is related to, now let's go back to elliptic curves. Then in the distribution, okay. Any question about this? So far, everything is elementary. And then, you have seen these things at some point of your life. So, and then we remember this. And then this gave us Catalan numbers. Actually, even like positions, Catalan numbers, odd positions are all 0. And the same thing happened here, exactly the same thing. So we are seeing that this is actually this. Conjectural. And one side is very arithmetic, and then the other side is it's a combinatorial algebraic. And then also random from random matrices. So somehow, and this is true for arbitrary elliptic curves. So elliptic curves and then number of points, marginal p, behaves randomly. In some sense.
When m is even, then it vanishes.
Yes.
In the right-hand side.
We
can explain.
It's even or odd. So
I'm saying it's odd.
Odd, it vanishes, and then the other side is also vanishes because AP can be plus or minus, so they cancel each other completely. So like first just AP average is 0. Then the third power that also average is exactly 0. Only even moment, even power survives, and then it gives us exactly 2. Good question. Okay, so and then this was observed by Sato and then Tate around 1963. As you know, Professor Sato was advisor of Kashiwara. Professor Kyu-Hwan Lee. Then Tate, Professor Tate has also a long list of descendants. And anyway, so they observed this around that time, 1963. And around 2011, all these mathematicians together, notably Taylor, Charles Taylor, proved this is actually true. This was conjectured around 1963. It was proved in around 2011. I believe Richard Taylor received the breakthrough award. Or some award because of this. Of course, Richard Taylor is had been famous for contribution to Fermat's last theorem, but it gave him another honor. But anyway, so this is considered as a big achievement. So
And if you drop the assumption on the elliptic curve, is it not true?
so elliptic curve.
So it's for a certain class of elliptic curves?
So we'll consider it in the next topic, but they believe for any the general philosophy is that any arithmetic object should be the same. So meaning that not only elliptic curve, if you consider any motivic object, then there should be some corresponding motivic and then some automorphic or some like analytic or probabilistic objects which describe and the distributions should be the same. And I think that's a philosophy. And this is going to be one example.
But for the types of elliptic curves?
Types,
Like
you mean
I
non-CM?
mean the assumption in the theorem, yeah.
Non-CM.
Assumption.
Okay. That's actually, I think the next slide. Okay, thank you. And then also, even if we replace elliptic curve with other motivic objects, then philosophically, we should expect a similar thing, but of course, those are big conjectures. So CM means elliptic curves whose endomorphism ring is larger than Z is said to have complex multiplication. CM, so non-CM or CM. In CM case, we have these sequences. And how do you obtain these sequences? The same way, but now this group is different. This group is much smaller because it's the normalizer of U1 inside SU2. Okay, and it was proven much earlier than it's a result of Harris, Taylor, and other people because it's a kind of degenerate case. But again, same scheme or same structure exists. A similar structure exists for CM curves. But probably this answers your question. Okay. Now let's move on to genus 2 curves. Because the genus 1 curve is understood very well. Genus 2 curves. So more generally, let's start with the genus G curves. Then we consider this zeta function. Okay. And here, important thing is what is this nk? Nk is the number of the points on C over this. So we consider the fp. So when k is 1, and that number of solutions over the finite field that appeared in the case of an elliptic curve. But in general, if you consider this, then it is well known that this zeta function has this form, and then this numerator is a polynomial of degree 2g with a constant from 1. Well-known fact. Then for C is an elliptic curve over C, then we have this special case. Then this AP is the AP we define, we consider it. And then N1 is the number of solutions over FP. So same thing, different notations. Okay, so this was the special case. Then now we are considering genus G curve. Okay. Then if we do this normalization, we are dividing this square root of P So we did that previously. We are doing the same thing. Then it is also known that the polynomial becomes this. It's palindromic. So A1P, A1P, and A2P, and A2P. Okay. Then it's arithmetic, and then I mean, of course, yeah. As in the case of an elliptic curve, now we want describe or we are interested the distribution of the moments of these numbers. In elliptic curve, the arbitrary elliptic curve, the non-CM elliptic curve showed us that Sato Tate distribution coming from in the end, the moments become Kevlar numbers. What about this case? So we can ask the same question. So nature generalization. So we do the same as we did in elliptic curve case, but we have many more numbers. So K was one, genus one, that's elliptic curve. And now it's genus G. So we have G many numbers. Then M goes from 1 to infinity. So it's a real sequence. So K is 1 to G, M is from 0, 1 to, and then goes on. And then you consider the. Now, of course, empirically, you can calculate.
I thought you said that there are finitely many primes that added reduction.
Oh, here, yeah, here. The
Then,
same.
even if you include the bad reduction, that function will get the same. No.
I think so. And then, yeah. Sorry, but to be, yeah, usually when I do machine learning, I just include bad reduction because it doesn't affect anything statistically. But I think it's the people, number theorists do this because of theoretical rigor. But in practice, yeah, you may include bad reduction. Actually, I also do that.
Can it be clear that this number doesn't depend on the threshold C?
No. So C is an elliptic curve. So okay, so here, it should be C somewhere, right? So there will be C, but the conjecture is again it doesn't depend on C. I see. It actually depends, but yeah, that's right. So the notation should have C somewhere. But as you can see, generically it does not depend, and that's again amazing facts. How come? It does not depend on C. Generically, or there are actually for elliptic curves, there were two cases. Here, it's genus 2, so we'll see more cases than just 2 cases. That's the difference. Again, yeah, that's right. There should be C. I suppressed that from the notation. So empirically, genus 2. Now, the right-hand side is T. Yeah, then K is 1 and 2. We see these numbers. Then generically, yeah, you always see these numbers. Then okay, now these numbers are not. Do you recognize these numbers? Okay, and then okay, there is a different case. Because in the elliptic curve, CM and non-CM, likewise here a different case, but generically, I think this is a generic case and this is a special case, and there are many other cases. So there are, it's known, it's proven that there are 34 different distributions for genus 2 curves over Q.
What's the meaning of 34?
34. I mean, we are considering the distributions, so 34 different distributions, as well as the random variable and associated distribution. We count the number of different distributions. Y34.
Yeah.
Y34. That's the nature of this game. Yeah, I don't know. Y34. It's a kind of classification. So it's like a number of sporadic groups.
Number of sporadic groups?
I mean, it's like in analogy.
Okay.
Why there are 27? 27 sporadic.
26.
26.
So if a curve is given explicitly, can we tell before we computing the moments? Can we tell which distribution, which category among 34 distributions?
Oh, yeah. So in CM and non-CM case, you can. How do you determine if the curve is CM or non-CM? Okay. There is a certain way that you dream. Here, I'm not sure if there is an analog of dream here, but you consider the endomorphism ring, and then you know. Yeah, so there is a lot of theory behind the whole discussion. Okay, any other questions? And then genus 3. Okay, we are considering arbitrary genus 3, and then x to the 7th power. And then now 1, 2, 3. These numbers. How many different distributions? Yeah, and then people worked very hard. In particular, Cadillac and Sutherland, probably Fitte did all computations. I'm not sure. Sutherland also, he's very expert in computation in number theory. So 3 people found out that there are 410 Sato Tate groups, abelian 3/4 for number fields. I think it's conjecture. Yeah, it's conjecture. But the genus 3 case. Anyway, I would say this is a conjecture, but they counted then 410. So it depends on the definition of the Sato Tate groups. They made some kind of axioms, and then this 410 is a number, fixed number. The question is, are those groups are really coming from genus 3 curves? Then it is a conjecture. But in any case, so that's the 410 is the size 34, 234, and 410. And then actually this is over number fields. Okay, number is different. But anyway, so that's about the size. 2, about 34.
And what is the Sato Tate group?
Oh, okay. So a good question. I don't think I have the slide here. So conceptually, the Sato Tate groups are basically the generalization of this SU2.
Oh, I see. So
And then the normalizer of this U1, because these moments explain the distribution of the curves. Those groups are Sato Tate groups, but Cadillac and Sutherland and Fitte, they look at the necessary conditions for this kind of groups for arbitrary genus G, and they they brought up some set of axioms. So formally, you can define Sato Tate groups to be some subgroups of a compact Lie group, which satisfy those axioms. Then they can be like an official definition. But conceptually, those Sato Tate groups should provide you these moment sequences, and then the moment sequences should be the same as the sequences from curves. Okay. Question? Any other question?
The numbers in the distributions, is it already a miracle that they are integers?
Yes, already. Because this distribution is AP over square root of P. So there is no reason that moments should be a integer. But once we interpret those numbers as like a random matrix of statistics, and then if those are related to characteristic polynomials of random matrices, then now it's kind of clear. The representation theory side is clear, but arithmetically it's like a miracle. And I mean, yeah, the equality is a miracle. Okay, where are we? Okay, and in the case of G equal to 1, yeah, the moment sequences are coming from random matrices conjecturally. So that's a generalized Sato Tate conjecture. That the distributions are asymptotically the same as those of the coefficients of the characteristic polynomials of random matrices in the Sato Tate groups. So we have not defined Sato Tate groups, but there are certain family of groups, and then you consider random matrix in the group, and then consider the characteristic polynomial, and then look at the distribution of the coefficients, and those are the same as these AKP coming from the curves. Oh, okay, that's the yeah, in like here SU2 and then the normalizer of U1 examples of something.
Question. So what types of groups show up? So you said they're all some subgroups of some compact Lie group. Is the compact Lie group always SUN or something?
Yes,
or could it be? It's always SUN?
Not SUN, but here. Yeah, USP 2G. Then accidentally, when G is 1, SU2 is USP2. Accidental. So what is USP2G? It's SP2G with this unitary condition. So unitary condition. Compact. Then here, informally, I just explained this. There is a certain set of axioms, and I will present the axioms here. And because we are considering, and now H is a subgroup of USP2G, this is a unitary and symplectic. So we have a characteristic polynomial will be like this. This is a palindromic again. Then all these coefficients are real numbers. Okay, and then we may consider CK as a random variable. Then we can define the moments. Again, mth moment. So m is from 0 to 0, 1, 2, and then goes on. And k is from 1 to 3. Okay, and so we know that the motivation comes from curves. But now just look at this. Just look at this. Yes, so these are coefficients of characteristic polynomials. Then can you compute this? So we remember that in SU2, this was an easy computation. And combinatorially, that was interesting. Yeah, the generalized Sato Tate conjecture can be described this way. So this was the elliptic curve case. Then yeah, we will see the definition of these groups. But, yeah, this is the reformulation of the conjecture.
So Sato Tate group is associated to each curve.
Yes, but different. I mean, there exists at least one curve. So this direction is right, and then also each Sato Tate group which satisfies those axioms, at least one up to the genus 3 case.
So there's no uniqueness?
No, there are infinitely many curves which goes to the same Sato Tate.
No, for each curve, there's only one.
Oh, yeah, of course. Okay, any other question? Okay, then you can describe the Sato Tate groups for genus 2 curves over Q. And yeah, mostly disconnected. The total number is 57. This is, I think, 34. And if we include everything, then 57. And everything means like number fields and abelian surfaces. Certain multiples of group 3. And then now, yeah, let's just think about these numbers, representation theoretically, and how can you compute this? And we want to do it once and for all. So because k is from 1 to g, and then m is from 0 to like infinity, or from 1 to infinity. So let's consider this. Yes, and this is the characteristic polynomial, but instead of a minus, we have a plus, but that's okay because gamma is a random matrix, and then minus identity is there. So we consider plus for convenience. So it's basically a characteristic polynomial, and then if you take the product, then this will appear as a coefficient of this. Xj is a variable. Yes. Then these numbers will appear as coefficients of this. So this is, well, if you can compute this, basically you compute everything. Okay, so then we can do it one by one, but this may be a better way to consider. Now, how can you compute this? Okay, and then H is one of these groups. So yeah, then
There is a question from Zoom audience asking, does Sato Tate group depend on the endomorphism group of the Jacobian of the
okay.
curve?
Yeah, that's right. So, who asked the question?
Sungmun Cho.
Yes. The answer is yes. 조성문 교수님 안녕하세요. I said hello.
안녕하십니까.
And then in collaboration with the Se-jin Oh, there, we computed the autocorrelation functions for all Sato Tate groups for genus 2. And then, so we computed this. Then the result looks like this. But interestingly, the result is this. So we have this character coming from SP to M. Okay, SP to M. And we have these numbers. So because this is kind of known, you can compute this using character formula or in many different ways. So, or type C or symplectic symmetric functions. And then it only has 2 parts. No, I'm sorry. It's not 2 parts, but 1 and 2. You consider as partitions. Of course, it comes from the fact that we are dealing with the genus 2 curves. And what are these numbers? If once we know, assume that we know this, basically the problem is computing these numbers. Okay. Here, yeah, I think I explained this. So the question is, what are these numbers? Then computed all of them. I double checked with the computers. I believe this is correct. Okay. And then what are those? But the details are not important today. But let's see how we computed this. So the proof may be interesting to you. So we start with this dual Cauchy identity. This is an amazing identity. Right-hand side, or this left-hand side is a product. Then the other side is product of 2 symplectic characters, and then you are taking the sum. And here, lambda twiddle is, this is the conjugate. And this is like a complement of the conjugate. So this is an amazing 건가? This is due to Jimbo and Miwa. Both of them are students of Sato. Then Roger Hawa. Then the Professor Samjin. Kim was a student of Roger Hawa. So, for relevant to us. I mean, the academic junior last year. Anyway, the usual dual Cauchy identity is this. So this is a symplectic version. This is a quite interesting identity. Okay, then how can we use this? This is the calculation. It's not difficult. So we want to consider this. We want to compute this. This is just a normalization where we start with that, and then this, because if we consider these as eigenvalues of a gamma, and this is the characteristic kind of a characteristic polynomial can be decomposed this way clearly because we know the eigenvalues, and then along with this you compute this by expanding this elementary computation, that you get this. Okay, and then here we use the dual Cauchy identity. That's the this is a highly non-trivial, and then we are integrating with respect to t's. So x's can be pulled out, then you get this. So at the end you get this. Okay, now what is this? Then H is a subgroup, and then these are characters, but characters of SP2G, and then G can be like 2 in our case, or more generally, it can be arbitrary G. So clearly, from sure orthogonality, this is nothing but a multiplicity of the trivial representation in the restriction of this representation to H. So all the other characters will vanish after integration because the symmetric functions are, the characters are basically symmetric functions. Symmetry kills all the terms, and then you only count the number of multiplicity of the trivial representation. Okay, then this has become very representation theoretic and combinatorial, and that's what we did. So the computation of autocorrelation functions goes down to computation of branch rules. But because H is not very standard in the sense of usual representation theory, the classical branching rules are not applicable. I mean, we need to have a new branching rules. There are people have been studying branching rules for a long time, but we consider some special cases, and then our H is vice versa. So one by one, we consider branching rules. So it turns out that the computation was very representation theoretic and combinatorial, and then we used all the tools available in our hands. And then in particular, we used crystals a lot. But of course, the details may not be interesting. And then our computation may be generalized to arbitrary genus, in particular genus 3. And so
Why do you say just to genus 3?
because that's the next case. Genus 2, we did it. Genus 3.
Why not arbitrary genus?
Okay. Yeah, we can do it. Yeah, arbitrary genus. Yeah, that's right. In that case, the classification of Sato Tate groups has not been done yet. So we should look at the curves first. Or, yeah, that's right. Or the axioms. Yeah, but it can be done for arbitrary genus. And then from genus 4, I believe like AI or machine or large scale computation should be involved because the number of Sato Tate groups would be thousands. It's already, it doesn't make sense to have it in a single paper. It should be like a database, computer assisted approach maybe.
So right now, something has to be proven for every Sato Tate. For each case, you have to do.
Genus 2?
Yeah.
So the generic case is open. So when H is equal to USP4, right? Like USP4,
Yeah.
that's a conjecture. But all the other cases have been proven because those are degenerate case. So you can borrow the power of the theorem, Harris-Taylor theorem for USP2, that they use theorem to establish the conjectures for genus 2 curves. The USP4 case, that should answer your question.
No, well, my question is, so you have to do this branching rule, but you have to do it for each of the 34 or 57.
Oh, yes. Yeah, and then that's actually 52. So we should- That's right. Then here is the one very simple example. Let's see what happens when tree is 1. Then you consider really the construction of the irreducible representation. SP2C is basically SL2C. It's low rank. Then unitary, the U1 acts in this way. So, but we want to have a trivial representation. So A should be equal to B. Yeah. So U1 module is generated by when A is equal to B. Yeah, and then this has a trivial character with the multiplicity 1 if and only if n minus k is given. So we have to look at the action generators or the group element. Of course, in this case, it's elementary. But I'm trying to show you what kind of computations we have to do. And then now, how do you compute this? Then this number is only the matter, but that number is just coming from the branching rule. So you replace that number with the result, then you get this. So then this autocorrelation function becomes this. Okay, and then this is a very easy case. And then because you can easily compute the special case when some special coefficients, you can obtain the moments of the sequences from the formula. So the other case is this. This is a disconnected normalizer of U1. But the decomposition is not difficult. There is one generator, J, then you decompose it this way. We have to look at the action of J. Then, because this action, V1 goes to negative V2, JV2, negative V1, can keep track of the actions. Then include that. Now it should be like a mod 4. Yeah, mod 4. Previously it was mod 2, not mod 4. So again, the point is, you have to keep track of the actions, and then you have to know the representation very, very explicit to do the computation. So that was the difficult part. You have to know the actions and everything very explicitly. Then for a certain level, they can be done using crystals. In some cases, crystals are not enough because crystals forgets about some certain things. But of course, crystals show the structure very clearly. In our case, for example, yeah, this A comma B is a partition with two parts. And then we know that this is embedded into this representation. But in order to do the computation, we have to know the exact image. Then we should be able to compute the action of a group element very explicitly. Again, sometimes crystals are enough. Other times that's not enough. And we need to do more. So for example, yeah, we have to fix bases, and then we really this kind of basis do the computation. And because A and B are arbitrary, we can use inductions. Then we have to keep track of effect of inductive steps. For example, here, the highest weight vector can be written in this way or this way. So here again, the details may not be important at the moment. But the point is, we have to go really concretely to keep track of all the details. But and then at the end, we made some interesting observations. So most of the Sato Tate groups are disconnected, and we can decompose the integral according to the coset of the identity component, and then over some cosets, the characteristic polynomials actually were independent. So, for example, here. I don't know if this is clear, but actually, yeah, you can see that the characteristic polynomial of every element in this coset has characteristic polynomial 1 plus x squared. So, combining all these things, we could obtain non-trivial identities of irreducible characters. So, for example, this. This is like alternating sum. We have the product. This may be known previously, of course. So this shows you some computation. Because in that coset, we have this. So you decompose the integral. And this part becomes simply this, and then you manipulate further, and then you get some identity. So we did that, and then and for many other cases, the previous one was very simple. Here, we could obtain more general identities. This is a symplectic character, and then some sums. Somehow, that becomes the product. For the sure functions, King found out something similar, but for example, that means for type A, this was type C, and then of course these are all new. So this was a corollary of our computation. Just further details. Okay, so that's what we did. Then thank you for your attention.